I will invite Kristian to the stage to give the first demo.
Excited to be here today. So I'm going to talk about my business that I founded with my co-founder Greg, who is here in the audience, and it's called Lucid Computing. Essentially, we see two opposing forces on the market right now when it comes to AI and AI security. There is this industry push towards sovereign AI. Global customers essentially ask, how can I prove my data and compute will never leave a particular jurisdiction unencrypted? And you see this push towards sovereign AI. Everyone wants their own data center. There are deals in the trillions being made abroad as a result. But secondly, regulators want national security and some degree of transparency. US regulators, on the other hand, ask, how can I stop US AI technology from ending up in the hands of adversaries? Because this is something that is happening regularly now. China's military and government has acquired a bunch of NVIDIA chips that are not supposed to be in China in the first place due to export controls. In fact, almost all frontier AI models in China are probably being trained with smuggled chips. That's a huge problem. The AI action plan that was recently released by the White House is trying to strike that balance. And that balance is exactly what we're trying to strike at Lucid Computing as well. What we're developing at Lucid Computing is sovereignty certificates. And right now, whenever you run AI inference or workload with a cloud service provider, it's more or less a pinky promise. It's a pinky promise that your data will stay where it's supposed to stay. If I select Frankfurt with AWS, I trust them that the data stays in Frankfurt. But what we are developing is a three-step thing. So we have a solution where you can install a confidential container using our platform. So this is a container that is encrypted and can run inside of the trusted execution environment of a particular AI chip. All of this infrastructure already exists. And then secondly, we can verify that this container is where it's supposed to be through a network of landmark servers. I will tell you more about how that works in the next slide. You could see it as a bit of a cellular subscription. It's like subscribing to Verizon or AT&T, but in this case, you subscribe to a network that can verify the location of a particular workload. As a result, you can get a proof, and the end users of data centers can get a proof that all of their data stays in a particular jurisdiction for a specific AI workload. So how it works in practice is that you have a AI chip and you locate where it is. What happens is that we have this network of landmark servers. Imagine that one of the landmark servers are right here in San Francisco. The chip can then use a private key to send a message to that landmark server. Then we measure the round trip of that message. So if that round trip is 4.4 milliseconds, then we know that the chip has to be in California because it is impossible for a message to travel faster than the speed of light. It puts a minimum radius. If we then have another landmark server somewhere else and that round trip 8.7 milliseconds, then we have a radius there as well. We can locate approximately where this chip is located. This doesn't require any new technology or pieces of hardware. This works with existing hardware primitives that already exists at all modern AI accelerators. So we believe that this is a market opportunity for several reasons. First of all, there is a huge push for sovereignty. Data center deals is being made all across the world. Just a few days ago, there was a $400 billion deal with the European Union. There was the famous $1.4 trillion deal with the United Arab Emirates. Everyone wants their own sovereign data center to assure the sovereignty of their AI-driven economy. Secondly, there are harsh regulatory penalties related to where data is processed. You have ITAR, you have GDPR, you have HIPAA, you have all of these regulations that mandates that data is supposed to be processed at a particular place. Lastly, we also have export control. The AI action plan that was released by the White House is mandating and recommending that industry and government together solves this problem of location verification so that chips are no longer smuggled to adversaries. So the way our model works is that we have a pricing per chip per month, similar like a cellular service. If you look at the export control regulations, that will roughly cover 12 million exported chips potentially. Our last few months since we launched or since we started the business has been quite intense with a lot of momentum. In our first month, we had our first product ready. We performed our first tests and we filed a couple of patents. Then secondly, in our other month, we started to work together with regulators. We have been giving briefings to Congress, both the House and Representatives and Senators as a part of the Chip Security Act. We have worked together with Kessler's team at the Bureau of Industry and Security around export controls. And we have briefed the White House and Department of Commerce about the fact that it is possible to solve this chip smuggling problem in a way that end users and customers appreciate. Secondly, we have built a strong sovereign AI pipeline. So when we go out there to these foreign large-scale deployments and talk to them, they see the value of our service, not just for export control compliance, but primarily because they can prove to their end users that an AI workload is happening where it's supposed to happen. They can prove sovereignty to their end users, which they see as very valuable. Some of those deals that we have in the pipeline are up to 50 million ARR deals. Basically, what has happened next in the next few months is that we make sure that there is one of these landmark servers that can prove sovereignty in every single data center on the planet. When the export control regulations around export location verification is rolled out, we will be essentially the default service provider. We already are, in a sense, because we're the only business that actually have a deployment-ready solution for this. End the presentation with 2 predictions about the future. Prediction 1. I think that most economic activities will be generated by AI models from compute resources. What I mean by that more specifically is that you have a bunch of compute as an input, you add a few AI models together with that compute from known model providers, and then you produce a bunch of raw tokens. And those tokens are, valuable tasks being automated in the world economy. But secondly, I think provable trust of each token will be one of the world's most valuable tasks. Can you prove to whoever is benefiting from this model where the model is being located, in what jurisdictions, what laws apply? Can you prove that the model is not trained using the data that I provide to the model? Can you prove the identity of the model and that a model has passed particular evaluations? We see ourselves as that trust layer on top of artificial intelligence and providing that provable trust from a hardware root of silicon. That's about Lucid Computing. I think we might have actually time for a bit of a live demo to give you a flavor of what it is that we have built. So here is our website, API documentation. You should totally book a demo if you're interested in this, want to build some cool apps based on location verification. But I'm gonna log in, and it's actually loading a bit slowly because I'm connected through my cell phone that is somewhere in the room. But essentially what you have here is a bunch of landmark servers. You have a data center here. So this is actually our test data center in Sunnyvale, California. That test data center contains a couple of chips. I'm gonna reload again. Yeah, but this is how you know this is real. Okay, nice. Yeah, exactly. Oh, yes, perfect. Now it loaded perfectly. So this was a connectivity issue. So essentially we have 2 H100s humming away in our test data center in Sunnyvale. So what I will do now is to just do a quick demonstration. So I will essentially ask for a certification of location, and I will instruct my GPUs to reject that verification. So that would be the equivalent of moving the chips somewhere else. So I'm actually going to run just a small script that does that, and hopefully the chip in the data center will Oh, yeah. So here it is, red, non-compliant, means that it might have been moved. So that's our live location verification. And the idea is that you can essentially implement this in any type of app where sovereignty is important and where you could want to prove to any third party that data is being processed and a workload is processed in a particular place. So that's essentially it. And yeah, look forward to hearing from you. Do we have time for Q&As as well?
Yes, a couple of questions.
Okay.
Oh, okay, quick one. I'm assuming I saw SDX, so essentially you're using PEs. The question literally was, you're assuming that you have routing as line of sight, which is a strong assumption. If you don't have routing as line of sight and your routing that changes, then you will have boundary conditions. How do you handle that?
You mean routing inside of through the public internet?
Yes.
Yeah, so essentially in the demonstration that we have right now, and I think my CTO could probably answer a lot better if I somehow up here, but essentially the way we handle as deterministic timing as possible is that a lot of these data centers are connected with private fiber. So we have, for instance, one box in one data center, and then we try to route through private fiber as often as we can to have deterministic timing. If we route over the public internet, more of a complex topology, so we need to send more requests, and we have our landmark servers and try to build a more accurate topology map over time, because there is a bunch of switches and weird things happening in between, and there is also a bunch of public data on network topologies that we're leveraging to get as accurate results as possible. Did that answer your question?
You kind of admitted the fact that it will be challenging unless you have an adequate.
Yeah, exactly. But the thing is that in the end of the day, almost all chips are being deployed inside of data centers that are often connected with each other. The exception being if you have a large deployment that is, for instance, air-gapped.
Yeah, so that's literally what I was about to point out to you. So the assumption here is you're making everybody who actually has illegal H100s, V200s, or RTX6000s, rack it up in the data center. To me, the adversarial model, that's a stupid assumption. And basing the fact that they will have a dark fiber to them, again, is not a best assumption. If you're thinking adversarially, right? Because you have to think adversarially. Because you are pretty much having a nation-state adversary, and you want to think really hard what your base assumptions are. To me, as somebody who worked in cryptography and security, that's a big open question.
Yeah, obviously it's a difference of the sort of trust guarantees that we can give based on where the chips are deployed. So if you have, for instance, a small deployment, most large deployments will happen inside of conventional data centers with good overall connectivity, but you might have a small Latvian university with 2 H100s, and then we have to ping through the public internet, and obviously the guarantees will not have the same gravitas. And I think in the end of the day, the United States need to have a defense in depth type strategy where our solution is one slice of cheese, if you will, if you're familiar with it.
Yeah. Very most stupid. It's like literally, you could have an extra board because there are DEs in there, and if you get on the bus, you could actually just run a GPS straight up. You can do the authentication, you can do the clock, and you could do a differential between every place in that thing, and you would pretty much nail the thing down. You don't need to do all of
I really want to talk to you afterwards, so we should have a conversation. Thank you for the great questions.
Okay, we have the mic.
Nice. I'll maybe also just plug a bit of your previous work too, Kristian, and ask you, so Kristian is the author of a book called The Dominion Trap and has previously worked in this field, carbon accounting, within the European Union as well, shaping these large-scale compliance mechanisms. And given this deep thought you've already had over the last 10, 15 years nearly in this field, what are some of the things you brought into AI safety and then you found work really well for you here?
I think one way to summarize my lifetime of work is that I enjoy patching externalities in the world economy, meaning that whenever you have pure profit maximizing, it doesn't always lead to the right outcome. So then you need to measure whatever externality is that you have patched and build standards around it and regulate. My previous company, Normative, grew that to 200 employees, but that was on a backbone of working on standards like the carbon disclosure standard, working on the greenhouse protocol standards, so actual standards for how to calculate carbon emissions. We implemented those standards into software, and we went out to regulators in the European Union and the UK, highlighting that some of these externalities that we're seeing can be patched with the help of technology. We built industry coalitions around those standards, and eventually regulators had enough confidence to make these things mandatory, and our company was the second fastest growing SaaS company in all of Sweden for multiple years. This is, I think, a playbook that I'm doing quite well, if I should pat myself on the back a little bit, essentially working on coalitions and standards and then regulators to patch risks and externalities. Great question.
And then a last question. Anyone else?
This isn't my area of expertise, so my apologies if you already answered this, or this is a silly question, but what exactly are you attesting to or verifying, right? Is it these chips live in this location? Is it the actual forward passes definitely happened in this location?
Yeah, so we're essentially verifying that it is within a particular radius based on the speed of light. So we don't know the exact location.
That's where the data was processed.
So that is the location of the chip. And if the chip has a secure enclave where it's sort of doing inference, then if we know where the chip is located, we also know where the AI inference is happening.
Maybe just a quick follow-up question. Yeah, how feasible is it to, I mean, it's obvious, but separate out the TV or whatever's talking to your thing and doing the ping from the other parts of the chip if I just cut my chip in half or something?
Yeah, so essentially our whole model is dependent on the hardware root of trust, so the private key of the chip, and this is printed in to the silicon die. So, yeah, sure, go ahead.
I published a couple of papers with the thing involved for a long while. So it's normally physically impossible to separate. Your security model will be broken if you can separate a TP.
Any further comments on that?
No, I think that was a perfect response.
Perfect. All right, thank you so much to Kristian. There we're giving him